So, welcome to today's community meeting. Today, I want to talk with you about this Restate's distributed architecture, which I believe some of you might already await, and we hope to ship it soon. It's a bit, let's say, lecture heavy in the beginning, but if you bear with me, at the end, you will be rewarded with a demo of what's already working. So yeah, but if you at any point, if there are questions or I'm going too quick over things, also just feel free to interrupt and ask a question. So since I believe that you already know a bit of Restate because you are here in this community meeting, I will skip the general intro and get right away to the topic at hand. As a quick reminder, I want to remind you where Restate sits as like infrastructure-wise. So Restate sits between your services on the right hand and your service users on the left hand and acts as a kind of mixture of reverse proxy, message broker database to do its magic. And it actually needs to sit in between the requests and the services to actually be able to record the requests, to enrich the requests, and to provide your services with the properties of durable execution, durable communication, and consistent state. And in today's session, I want to dig a bit deeper into how this works under the hood in a distributed setup. But before we get to it, I quickly need to introduce two concepts that we will meet at various places throughout the session today. The first thing is, how do we actually achieve horizontal scalability, and what are these partitions everyone is talking about? So in Restate, every invocation you do has a key. Either it's the key that you as a user specified when invoking like a virtual object, like where you put it between the service name and the handler name, or if it's a service invocation that you're doing, it's a randomly generated key that Restate does for you. And this key is hashed to a partition key. And this partition key is just a plain U64, but these, like the values of these partition keys form like the partition key space. And this space is range partitioned into partitions. And those are the units that we assign to workers to work independently on. And so if you have a couple of these partitions and a couple of nodes, you can distribute them and let the different nodes work on each partition separately. The other concept that you will encounter throughout this presentation is how do we actually achieve fault tolerance? There are several ways to achieve fault tolerance in distributed set systems. One popular one is using replicated state machines. And Restate is one of them. The idea of replicated state machines is that every state-changing action that happens in your system first gets recorded in a replicated log, where it's durably stored and order is established. And then these events or actions are consumed by a state machine. And if the state machine, the logic of the state machine is deterministic, then you can have multiple replicas of the state machine that will all end up at the very same state after they have consumed the log up to the same point, because they will all consume and see the same commands in the log in the same order. And since the state machine logic is deterministic, it's guaranteed that they end up at the same state. So if one of these replicas fails, you can just switch to another replica and see the same state, given that it has reached the same point as the previous replica when consuming from the log. That's also more or less how Restate handles fault tolerance, as you will see in a few minutes. All right, getting back to Restate. So Restate consists of two parts, if you wish. The one part is the application code that the user of Restate provides and which Restate invokes. And the other part is the Restate server. That is was the blue box in between the users and your services on the first slide. The Restate server can be broken down into roughly 3 parts. There's the control plane with the metadata store that is responsible for controlling what happens in the cluster. It's responsible for storing what are the registered services that you can invoke. And also it offers some admin APIs so that external users can actually instruct the server to do something or to inspect it. The second part is the fast durable lock, which is essential to Restate's proper functioning. Because it's a replicate state machine, we need somewhere to store our state-changing events. And that's exactly happening in this part. And the state machine part is the processor. It contains the business logic of Restate, which is handling incoming invocations, making sure that for a virtual object, for example, only a single invocation for a given key is invoked at any point in time, making sure that if a failure happens, that we actually reschedule the invocation and provide the right journal to the invocation so that it can replay properly. And last but not least, once the invocation completes, sending the response back to the ingress and then to the external client. If we zoom in a bit more into a setup where, let's say, we have 2 worker nodes running, worker 1 and worker 2, how would the invocation path look like? So it starts by an external client making an HTTP request to the ingress, and the ingress would then do the following. First of all, it will figure out which is the partition responsible for handling this invocation. So it will compute the partition key and look up the partition that is responsible for this partition key. Next thing it does, it will figure out where the partition processor responsible for this partition is running. And more concretely, since you can have multiple instances or like partition processors, it will look up the leader, the leading partition processor to talk to. Once it has figured that out, it will send the invocation over via an RPC request. Before the partition processor can act on this invocation, it first needs to durably store it so that in case a failure happens, another partition processor can resume this invocation. So what it does, it writes this invocation to our durable lock, also called Bifrost, to which all the worker nodes have access. Once the invocation has been durably stored there, we can actually update our internal state, for which we use RocksDB, and then start with, depending on whether we can obtain the log for this service or not, start the invocation. And this usually entails opening an HTTP toStream to the service endpoint, streaming the request there, and receiving back the journal entries that the execution of the service generates. And as those journal entries are received, they will also get written to Bifrost before they can be acted upon. And once the service invocation completes, the partition processor leader will be able to send the response back to the ingress as a response to the initial request if it's still open, when the ingress is, or the external client is still interested. In order to avoid that in case of a failover, we have to replay all the events from the very beginning of time, which can, depending on how long Restate runs, be substantial. We periodically create snapshots of the partition store and upload it to S3. And this allows us to recover quicker by downloading the snapshot and then only replaying the log diff that happened since the snapshot was created. That is basically part, like the second and third part of what I've shown you on the slide before. But then there's also the control plane part, that's responsible for selecting who is the leader for a given partition and which node should run which partition, for example, or how is the lock configured. That's the responsibility of the control plane. Interesting bit is that the control plane itself is more or less stateless because it keeps all the relevant state it needs for its proper functioning in a durable and strongly consistent metadata store. All right, let's zoom in a bit on the partition processor, the component responsible for the business logic, and which is also the component like the state machine in the replicated state machine model. So the partition processor consumes from the durable log the events and applies them. In essence, it is a big event loop. Whenever a new event is written to the durable log, for example, an external client making a new invocation, calling the ingress writing to the durable log, this would basically end up on the partition processor, which then would take it, update its internal state, and apply it. And depending on what kind of command it is, different things can happen. For example, let's say it is a delayed invocation, then it would register a timer so that when the invocation should be executed, a timer would fire and would notify the partition processor about it. If it's a normal invocation and there is no other invocation for this key ongoing, then we can directly invoke it. The partition processor would do this by using a component called the invoker, which is the component talking to the Restate SDKs. The invoker would then open, ideally, an HTTP2 stream for efficient streaming the request to the service endpoint and receiving the journal entries back. But it can also, in case that your deployment target doesn't support HTTP2, it can fall back to HTTP1 request response style communication, like when deploying on Lambda at the moment. You can have hundreds or thousands of these partition processors, depending on how many partitions you have configured. You can even have multiple partition processors responsible for the same partition. In that case, though, there must be a single partition processor that is the leader, because these partition processors, as part of their business logic, they need to interact with the external world, like invoking the invocation, for example, on the service endpoint. And let's say we are running partition processors for a given partition in order to have very low mean time to recovery in case one of them dies. Then we certainly don't want them that every of these partition processors invokes the service, because it can inflict costs, for example, when invoking a Lambda service. So that's why there must be a leader, and this leader is the component that can interact with the external world. The important bit, though, is, or a noteworthy bit here, is that there is, between the partition processors, there is no explicit coordination. So the bit where the coordination happens is Bifrost on the log level, not on the partition processor level. And that makes them really efficient and makes a scalable system possible. Okay, let's talk about the distributed log, or the durable log that Restate comes with. Before I mentioned internally, we call it Bifrost. So if you happen to fork the code base, if you look for the Bifrost crate, there you will find all the interesting bits. Maybe the first question to answer that might come to your mind is, why are they implementing a new log? Why can't they use an existing one, something like Kafka, for example, or Pulsar? The reason why we set out to build our own log, or yet another distributed log, is that the existing logs didn't fully satisfy our requirements. So in order to make execution really usable for services that might also sit in the hot path between a user interacting with a web application, not only for high latency workflows, this needs to happen very quickly. The log is the factor that determines how quickly we can make progress, because we can only make progress as things are durably stored in the log. Kafka didn't fully fulfill this need, and also it comes with a bit of operational complexity with static partitioning, for example, just not what we needed. Same for Pulsar, that comes with external dependencies like Zookeeper and Bookkeeper, where you now, if we use this system, would ask our users to also operate these systems. But we wanted to give a single binary, all batteries included experience, which makes operating Restate very simple. And other alternatives like Redis or RabbitMQ disqualified themselves because they didn't offer us like durability that we needed. So that's why we set out to build our own variant. And as the log is the primary source of persistence, it's really essential that this thing works correctly, because if we lose log entries, then the system won't be able to behave correctly. So the log needs to give us durability so that we don't forget about them, and it needs to establish order. That's required for the replicated state machine part. So every reader needs to see the same order of events, so that in case of failover, where one partition processor dies, another one can take over and continue from where it left off. And yeah, those are the requirements. And we build it not only a distributed log, but a distributed segmented log, which means that the log consists of segments that are can be backed by different log implementations. In that sense, it follows the design of virtual consensus and Delos, which is a paper that proposes how to virtualize consensus for systems that need it. And in essence, the idea is the following. Like as a user of a log, you don't really need to know what is the backing implementation behind it. Like a system that like needs consensus. What's enough for it is I want to read from log sequence number X to X plus 10, for example, and that's it. So a bit similar to the idea of virtual memory, Delos proposed to introduce like a virtual log sequence number space that can be backed by different log implementations. And as the MMU translates from virtual to physical memory address when you access it, the Bifrost layer would do the same for you. Like it translates from a virtual log sequence number to the actual sequence number that tells you where the data is and from where to get it. And this has some interesting properties. One of them being that it's now quite easy to seamlessly migrate from different loglet implementations while the system is running without shutting it down. And similarly, if you just need to change the configuration of a loglet, this also works seamlessly. The thing that needs to happen is we need to seal the previous loglet and then update the metadata to tell the users of Bifrost what is now the tail segment. So which are the nodes I need to talk to make a write or read happen. Moreover, with this design, the actual loglet implementation can be simplified significantly. Because we no longer need strong consensus on the data plane. Many of the tasks that a distributed log needs to do, like electing the leader, managing the cluster membership, monitoring its health, and reconfiguring itself, can be pushed to the control plane of Bifrost and kept out of the loglet implementation, and thereby significantly lowering the requirements of what you need to implement. So in essence, what this loglet implementation needs to give us is, I mean, apart from the replication logic, it needs to give us like a fault-tolerant atomic register, which allows us to store whether it's sealed or not. But the consensus part is now part of, or can first of all be shared, and is part of the control plane of Bifrost. So the loglet we are currently developing is called the replicated loglet. And the idea of it is that we wanted to have in a stable state of the cluster a very efficient, fast path. If something bad happens, for example, that would require reconfiguration, like we lost a node, now the log needs to run somewhere else, that this would be escalated to the control plane that takes care of finding a new stable configuration from which we can continue afterwards. The actual implementation works the following. So a replicated locklet consists of a sequencer that can run on any of the restate nodes and is responsible for receiving all the write requests that should happen to a given lock. The job of the sequencer, as the name indicates, is to order these requests and then to do quorum writes to a set of nodes, which is part of the configuration called the node set. And doing quorum writes allows us to be give high write availability and tolerate some node hiccups quite nicely, because we don't require that every of the nodes in the node set stores every record in the lock. Just we require that there is, for every given record, there is a write quorum, so a certain number of nodes having stored this, so that in case of a failure, we can actually, we don't immediately lose it. We can still have some replicas and read it from there. If now a failover needs to happen, because, for example, the node on which the sequencer runs died, then what happens is that the current lock will be sealed. Here, basically means that we tell this lock that it shouldn't accept any future writes anymore, so that if there's a straggler or some pending writes, they would be rejected. And sealing to make this happen, achieving read quorum is enough, because any write quorum would intersect with the read quorum and therefore would be rejected if the locklet is sealed. And once this happens, we can actually, or the control plane will instantiate a new configuration, where it, in this case, might place the sequencer this time on node 3 and continue from there. All right. Now, having talked about the failover case and how the lock is implemented, let's piece it together with the other bit of failover that needs to happen, which is the leadership of partition processors. So the cluster controller is the component that is responsible for detecting and orchestrating the failover behavior. The cluster controller runs as part of the control plane and is stateless. All the state that it needs is stored in the metadata store and can be retrieved from there. The cluster controller periodically heartbeats the restate nodes, and thereby it can determine whether a node is still alive or dead. And if, for example, node 1 here is detected to be dead because it missed a couple of heartbeats, we need to reconfigure the system. And one bit we've already talked about, which is we need to actually move the sequencer to a different node to reestablish write availability to our lock. In that case, what needs to happen is we need to seal the current locklet and write a new configuration, establish a new configuration for the next locklet, where this time the sequencer is on node 2. And in case the partition processor leader is also on the node that died, we need to move that one as well, because we have said in the beginning that only the leader is the one that can act with the external world, concretely invoking invocations. So without a leader, nothing would happen in Restate. The way this works is that the cluster controller tries to collocate the partition processor leader with the sequencer node, because that way the writes and reads to the lock are more efficient if it's collocated, because of some optimizations that are happening. Now, once the cluster controller has found a suitable node where the partition processor leader can run, it will instruct this node to make this partition processor the leader. And the way this specific bit works is that the partition processor announces its leadership. So first of all, it gets a leader epoch from the metadata store that is monotonically increasing, and it will announce this leadership epoch on Bifrost. And by proposing or announcing this leadership through Bifrost, we gain another nice property that, first of all other nodes learn about it, like all other partition processor replicas learn about the new leader and can fence off older writes that originate from a now outdated leader. And this outdated leader will eventually also learn about there's a newer leader because I've seen a message with a higher leader epoch and can step down. And that way we guarantee like strong leadership for partition processors. All right. So far, so good. Now I have, I think, 3 more things before we can take a look at the demo. The first thing is I wanted to tell you a little bit about how Restate uses object stores to offload state and why this is important. So the reason why Restate tries to offload its states to an object store is that the more state a system needs to manage, the harder it is usually to operate. Imagine, for example, like a stateless system that keeps like terabytes of data and replicates it across its own nodes. And now, like one of the nodes dies. Now, all of a sudden, the data might be under-replicated, and you are at risk of losing data if, for example, another node dies. So now what you need to do, you need to repair or reestablish the replication. So ship a lot of data from the existing nodes to either new nodes or to the existing nodes. And the larger the amount of state is you need to repair, the larger the window of risk of losing data is. So if there's a cascading failure, it might put you at risk of losing data then. That's why Restate tries to offload its data to a system that is even more durable than Restate itself, which is an object store like S3. So what we do on the partition processor side is that the state that is stored by the partition processors is stored in RocksDB and is periodically uploaded, or like a snapshot of this state is taken, periodically uploaded to the object store. RocksDB is actually, as a tree-based key-value store, very well suited for that because it also supports efficient incremental snapshots where we only upload the newly created SST files and not the whole data over and over again. And with these snapshots, we can actually trim the log because we don't need the records from before anymore, because we can just download the data from the object store, instantiate the partition processor, and then start consuming the log from a later log sequence number than from the beginning. The logs themselves, there we also want to leverage the object store. And the idea here is that, like, while we believe that in-band replication between nodes is required to achieve low latency, we think that by batching the recent writes and uploading those data to S3 is helpful as well, because that way we only keep the very latest tail of the log replicated between the restate nodes, and everything else can be retrieved from object store if needed, which in the normal case where all the partition processors are properly tailing is not needed, but as a safety measure. All right. The other bit that I want to mention is how we envision scaling out. So we talked initially about that the partition is the work unit that you can spread across nodes. So the more partitions you have, the more you can distribute the work that Restate needs to do across multiple nodes. However, there are situations where one invocation or one service wants to call another service. And this, let's say, this specific invocation that you're sending is executed by a different partition. If you just have a single partition, it's actually quite easy to ensure that this invocation happens exactly once. You take a log and then run it. But if you now need to talk to another node where the actual partition that is responsible for this invocation is running, you need to make this communication reliable and exactly once. And that's the job of the shuffler, yet another component that the partition processor runs, if it's the leader, that makes sure that the data is exchanged in a exactly once fashion. And the way this works is by assigning a monotonically increasing sequence number to messages that it sends to the other partition, and thereby the receiving partition can deduplicate messages and can make sure that a invocation happens exactly once. Right now, when you start the cluster, you need to determine the number of partitions upfront. And right now, it's no way to change it. So it effectively limits a bit your maximum parallelism you can scale the system to. But in the future, what we want to add is support for dynamically splitting and merging of partitions to support dynamic scaling in and out, depending on the actual workload that you need to process. And this brings me to the last point, which is now we've talked about all these components and how does this all fit together with the self-contained single binary that comes with all batteries included. And the way it actually comes together is that the single binary comes with all components. It's just that depending on which roles you configure to run it with, it will start some of those components and some others not. In the single binary, all batteries included case, by default, you will start all the different roles that will run all the different components we've talked about. For example, there's the ingress role that runs an HTTP server opening on port 8080 to receive the invocation requests. Then there is like the admin role that runs the cluster controller and also opens port on 9070 to give access to the admin API. And same for log server and worker. If you just download the binary and run it, they would all be started and run. But if you need to scale these things independently in the future, that's also possible. You can actually configure the Restate server to just run, let's say, the log servers, and those you can then deploy on hardware that's optimized for high write and read throughput, for example. Whereas the worker role, which is a bit more compute intensive, you can put on machines with stronger CPUs. So while it comes in a convenient package, it's still designed to give you enough flexibility to also run in more complex scenarios potentially in the future. And with that, it's finally time for some demo. So let me switch to my terminal. All right. Okay. The first thing I need to do is bring up a distributed Restate cluster. And for that, I've prepared 4 configurations that I will start here. So concretely, the setup I want to show here is that I run one node, the node 0, that runs the admin and the metadata store role. Then I have 3 other nodes, node 1, 2, 3, that run the log server and the worker role. And that should bring things up. And as you see, they start some partition processor are being started on all the 3 worker roles. And to further inspect what's going on in the distributed cluster, we have actually developed a new command line tool called Restate CTL that you can use to inspect what's going on in a cluster. Currently, it's not yet like released as a binary, but you can just build it from source. So the first thing we can do is take a look at what nodes are part of our Restate cluster. And here we see the 4 nodes that I have started. Node 0 runs our admin and metadata store. And nodes 1 to 3 are our log servers and workers. Next, we can take a look at our logs. One thing I didn't mention yet is that we create a log per partition. So every partition processor has its own log to which it writes and reads from. And if there's like cross communication between 2 partitions, then one partition processor needs to write to the log of the other partition to make the communication happen. So let's see. And here we see we have apparently 4 locks, which means that I've started the cluster with 4 partition processors, which is correct. We can now also take a look at the partitions themselves. And here we see, first of all, a lot of nice color, which is nice. And we see that we actually have 4 partitions, like 0 to 3. And every partition is running on every node. So we see node 1, 2, 3 are all running partition 0, 1, and 2, and 3. This is currently how the system is configured, that by default it will spawn partition processor on every available node. In the future, there will be this will be different and give you more flexible options. What you also see here is, sorry, that there is, for every partition, there is a leader. And in our case, only partition 3 runs on the leader on node 3. Every other leader runs on node 1. Fair enough. And then we have some more information. One being what's the epoch of a leader that we've observed, on which node is the sequencer running that is responsible for the lock for this specific partition, and what is the current applied LSN. The applied LSN effectively means how are we in applying the records from, or the commands from the log. So as you will see in a second, as I create invocations, you should see that this is increasing as we process them. Yeah, so let's maybe do that. So first thing I need to do is I need to start a simple app. The app itself is a counter service that allows me to add numbers, and it keeps the current value in its state. So it's a virtual object, so it's keyed, and I can increment this number. So let me register that. Yes, all right. Then let me actually watch the status of our cluster so that I hopefully see something happening as I do some invocations. One thing I forgot to mention, all of the 3 worker nodes also expose the ingress on port 8081, 8082, 8083. So I can do something like that. Let's see what's happening. Okay, if I add 1, so apparently we start with 0, so it's 1. If I do this a few times, I see, right, I do see a few things. First of all, I see a incrementing number, which is great. But I also see here in the cluster overview that the applied LSN is increasing. So it means apparently that the invocation for counter 1337, that's the key. The add invocation is processed by partition 3. Great. That's something we have learned from this overview. Now, let's maybe take a look at generating some load. Here I have just a small script that randomly creates a key and sends the add invocation. As you can see, what's happening is that it's random enough that we actually spread across all partitions, and they seem to make some progress as the applied LSN is increasing. So this seems to work. Great. Now let's maybe try to look at what happens if I kill a node. So first thing I want to do is want to see where we are with our 1337 counter. So we are at 11. And remember, this key is processed by partition 3. So let's actually kill our current leader of this partition processor and see what's happening. So it's node 3. I need to kill that one. That should be this window, I hope. Let's see what's happening. Let's go back quickly. Okay, so apparently we have detected that node 3 is dead. And here, not sure whether you spotted it, but there was for a short period of time, we've seen there's like the node 1 transitioning state from follower to leader. And now it actually became the leader. Cool. So that's interesting. one other interesting aspect we see here is, okay, now we have a new locklet ID. It's 3_1, and we start from LSN 1016. So this is actually an indicator that we also needed to reconfigure our log for partition or for partition 3, and we can inspect it in a second. But the first thing I want to make sure is that we can still haven't lost any information. So let's actually add another number to our counter 1337, and it's 12. So if we add 1 to 11, it's 12. So it seems to be correct. So that seems to work. So even though the old leader has died, the system recovered, remembered the state, and can continue working. Let's now take a look at, well, maybe let's first bring up the node again and see what happens then. So we have restarted it. Okay, now we see that this node apparently needs to catch up. So because it was down, it missed some of the commands from that are stored in Bifrost, and so it needed to first catch up, reapply the commands that happened while it was down. And after it was caught up, it has become a normal follower, being active, and now participating again in the logic that Restate is well, and in the proper functioning of Restate. So let's inspect now. I want to show you this log now. Let's look at the logs and describe 3. So here we see that that's the configurations of the log 3, and we see that the first segment started from LSN1, and the configuration was that the sequencer was running on node 3. But since we killed node 3, the system needed to reestablish or reconfigure the log, so it needed to seal it and move the sequencer to somewhere else so that we reestablish write availability. And that are we seeing here, that we sealed it on LSN 1015, I think, and 16 is the next one then. And this time the configuration is that the sequencer runs on node 1. Yeah. Last thing I want to show you is just that, well, let's see whether the demo gods are merciful. I want to run the random adds script and kill a node and bring it up back again, see whether we actually bring the system down or not. So I start my random adds script. It's doing something. And now let's kill a random node, 2 this time. One thing we see here, but this is not to be confused, is that request to port 8082 fail, which is the ingress that runs on node 2, because I killed it, and the script is not clever. It just randomly chooses one of the 3 available ingresses. Those will fail, but everything else seems to work fine. We see we're making progress, and that's good. Let's bring the node up again and see whether it will actually recover. Yep, seems to work. Yeah, I guess I can repeat this, but probably there's not a lot of, well, it's not really interesting. So let me stop it here. And that was basically the demo that I wanted to show you about the current progress of what's already working. And what you've seen is a fully distributed setup. Theoretically, I could have deployed those nodes in 3 different regions, and with Restate's replication mechanism, we would get like cross-region or geo-replicated system. Let me get back to my last slide, which I guess, 1 second, here we go. You might be interested in. When can you actually use that? So a lot of work has went into the distributed architecture, yeah, there's a lot of upfront investment to make this right. I think we are quite close to ship an early version or preview version of the distributed architecture very soon. Just to give you an overview, what's missing is the following. We want to be able to support trimming of logs for one reason, to avoid unlimited growth of what you store on the log, which is the main reason. That is still, I mean, I think as of today, some of the PRs actually were merged, so maybe that's almost done. I think for a proper functioning distributed setup, we need a highly available cluster controller. Part of the reason why I have set up the system as I've demoed it with the separate cluster admin and a metadata store role is that the cluster controller is not yet fully highly available, but there's a PR open that will add this functionality. To make use of the log trimming, we need to upload or create state snapshots of the partition processor state store, because only if we have this data, we can remove records from the log. Otherwise, we might risk losing data. Luckily, like the first PRs for this feature are merged, and we hope to complete it as soon. And last but not least, we want to add an embedded, highly available metadata store. The reason why we think this is important is that it makes the story of a single binary, all batteries included, makes the story sound. At the moment, I mean, technically the metadata store is pluggable, and we have an implementation for etcd. So if you're willing to deploy etcd, you could use it with that. But we want to have like a variant that runs embedded to give a nicer experience. And we hope that we can complete this plus the some smaller bits by the end of this year, beginning of next year, to ship this feature of distributed restate to you. And with that, happy to take any of your questions.
I have a quick suggestion just to torture this demo a little bit more and maybe potentially embarrass ourselves. Should we? I felt that you're a little bit too gentle, and I think we should demonstrate that we're a little bit more resilient than this. So maybe one thing I would love for you to demo is actually killing more nodes such that we actually lose write availability and we cannot make progress, to just show that the system will protect its correctness if it cannot establish quorum. All right, so invocations will just basically pause, and then once you bring nodes back up, it should actually continue automatically. So and a leader action works. So I think it would make such a good demo. So if possible, if you can do it, hopefully, fingers crossed, everything works.
I certainly can cause chaos. Let's see, it's still all running. So this is okay. Then I guess let's start our random adds and kill 2 nodes.
You don't have to do the random. I think it's just pick a key, for example, so we can easily see the values, like no correction problems here. Yeah,
it's currently 20.
Yeah.
So let's kill node 1.
So just to highlight for everyone here, because I don't think you mentioned this explicitly, the cluster is configured to have a replication of 2, which means that it requires 2 log servers, like 2 nodes, to be alive in order to actually make any writes for write quorum. So losing 2 nodes means that we will not be able to write.
Yes. So now I'm sending the request to the remaining node, node 3, which should listen on port 8083. And we see not a lot is happening because as of what Ahmed said, that we cannot write to Bifrost, which is the prerequisite for the partition processor to start working on the invocation.
Can we see the logs?
We can see the logs. It's on info.
Yeah, but you can see here, like, keeps trying.
Yes, it retries, but it keeps failing. So this is happening. All right. Let's go to the bottom. Now let's restart the node and see what happens.
We only need one extra node to bring this back to life. Yeah.
Let's go back here. See whether we get a response. Okay, something catching up. 21.
I think that's impressive.
Indeed.
Even your curl didn't fail, basically. So your you pick a random node, you curl to it, and it's still kept. Actually, it's just a single request. That node kept retrying to write to Bifrost, and if once it was able to, no duplicates, nothing, right? So the counter increased exactly once, as expected. So basically, a distributed counter service nowadays.
Yep. And if you want to try it out yourself, this is basically main that I demoed here. So yeah, you should be able to reproduce that with the current main.
Yeah, a lot of questions on consistency and how the different components interact. I think one aspect is the consistency of the metadata store itself, which underpins the control plane's decision making, and that's quite crucial. And I think a fundamental aspect of the architecture is that separating the consistency properties of the metadata store allows us to use flexible quorum for the log, which reduces latency, increases throughput, and availability. So, perhaps one question that I was hoping to see that I don't think we touched on is that we will fully support starting with a single node co-located local only deployment and evolving that towards a disaggregated cluster setup with different nodes running multiple roles.
Yes.
There's a way for it, yes. Technically, I think it might even be possible to start from a using the existing local loglet that only supports like single nodes, and reconfiguring it to a single node replicated loglet and then scaling out potentially.
Well, I think that's the plan. So you should be able to start with a single node, no dependencies, and then once you need to migrate into a cluster, just starting more nodes, configure them, and you don't need any migrations. So the system should automatically scale, and any data that needs to be replicated will be replicated automatically. But we also do like one important aspect as part of how the system is designed is that we have 0 copy reconfigurations. So when you do reconfigurations, like if you add nodes, or like when a loglet gets reconfigured as part of the failover, we don't actually need to copy the previous data. So for example, if you scale from one node to more nodes, it doesn't mean that we copy all the historical data from the previous nodes to the new ones. The snapshots that will be uploaded to an S3 compatible data store or object store will include everything, but you don't need to copy the history of the log, which makes reconfigurations cheap and quick.
So performance-wise, I think there's a lot of possible improvements that we can do. While the replicated setup adds some latency when it can add some latency when it needs to write do the Chrome writes, it can save some other time that we currently need to do for f-syncing if you're fine with just keeping data replicated, not strictly synced to disk where it can save time. So that's definitely will be a config option. Personally, I would hope that we can maybe not cross-region, but for, let's say, same as or so, do something like a similar ballpark as the current latency.
I hope that in the, well, sorry, just to add a little bit more color, our priority is that first we need to get it correct. Second is make it fast. So correctness is our key focus. Just getting consensus right is difficult. Something I've spent many years working on. So that's the first priority. But I share Till's hope is that we hopefully in the first iteration, hopefully it's not going to be worse than the single node. Hopefully.
Yeah, I was just wondering if there's anything that you expect to be able to get there, like no hard blockers. because I think that very low latency is quite important to some of the use cases.
Yeah.
That where you can have restate in the hot path. I think that changes a lot of things. So.
Mm-hmm.
Actually, longer term, the vision is to be lower latency than single node, just for various reasons. But one of which Till already mentioned is that because you can run on multiple nodes, you can afford to say that because I have 3x replication, for example, I can do that in memory because I have a very low chance of losing 3 nodes simultaneously, like physically crashing, and then syncing in the background.
There are going to be many interesting engineering challenges lying ahead of us in this regard, I believe.
But from design perspective, it's like everything from the ground up is engineered for low latency, like the logly design decisions, like everything basically is tuned for this. It's a very deliberate direction that we want to keep this low latency, and we don't want to compromise on that.